Okay, so for this problem, what we're going to do is we're going to look at two different functions that try to answer the question, what's the minimum number in a particular list? And you may have found this problem somewhat challenging simply because it's almost hard to think of a function that's n squared because it's hard, it's dumb. It's not maybe even the first natural thing, particularly if you've been through a CS1 course where you may have already written the linear function, and so now it's hard to think of another way of doing it. But before we get to the code for our n squared algorithm, let's just talk about it a little bit. So let's look at, let's just suppose we have a list over here. So we'll make a little list, 5, 4, 2, 1, and 0 will be our list. Okay, so now the idea of this n squared algorithm is simply going to be we are going to take the first number on the list and let's ask the question, is 5 the smallest number in the list? Well, in order to answer the question, is 5 the smallest number in the list, we have to compare 5 to 4, and 5 to 2, and 5 to 1, and 5 to 0. Well, so if we assume that 5 is the smallest, then if we find a number along the way here that 5 is greater than, well, then we know that 5 isn't the smallest. But that doesn't tell us what the smallest is. So the next thing we have to do is we have to ask, is 4 the smallest? So we'll check and see, is 4 greater than 5? Nope. Is 4 greater than 4? Nope. Is 4 greater than 2? Yep, 4 is greater than 2. So 4 is not the smallest. So we'll move on. And we'll go to 2. Is 2 the smallest? So we'll look at, is 2 greater than 5? Nope. Is 2 greater than 4? Nope. Is 2 greater than 1? Yep, 2 is greater than 1, and 2 is greater than 0, so we know 2 isn't the smallest. So then we go on and we do the same thing with 1. So you can see we're going to have to go through all the numbers on the list here before we finally get to 0 at the end. And is 0 greater than 5? Nope, 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 nope. Okay, so finally now we've got 0 as being the smallest item in the list. So that's our order n squared. We're going to compare every number to every other number on the list at least once. So let's take a look at what the code for that looks like now. And we'll bring up PyCharm. And so we will define our findmin function. I think I'll get this moved over to the side a little bit out of the way. All right, so def findmin, and let's say that findmin is going to take a list. All right, so we want to know what the overall min is. So we're going to create a variable called overall min, and let's initialize that to a list sub 0. It has to be initialized to something. We could make up a really big number that we know isn't going to be the min, or we could do something like that. But just picking one of the numbers on the list as our initial guess is an okay thing to do. All right, and so now here comes our list. So for I in a list. Okay, so we're going to loop over all of the numbers in the list I. So that's just like we were doing over here. That's going to be this kind of outer loop where we're going from number to number. And so then inside this loop, let's set up a variable here called is smallest, and we'll make that equal to true. All right, and then for j in a list. So we'll ask the question, if I greater than j, then is smallest equals false. So, as soon as we find a number where I is greater than another number, in this case, if we go back to 5 over here, 5, we can say 5 is greater than 4. So as soon as we say 5 greater than 4 is true, we know that 5 is not the smallest So we'll set is smallest equal to false. All right, now what do? When we're done with this, J loop, we can then ask the question, if is smallest, and if that's the case, if is smallest, then overall min is going to be equal to I. And then when we're all done, we can say return overall min. All right, so let's try to just test that with a couple of things. Let's try find min, and let's use the list that we used just a minute ago, 5, 4, 2, 1, 0, and let's print that. And so if we go ahead and we run find min, oops, not find mind, although it may be the case that I have lost mine, so that would be a good function to have lying around some days. Let's try running it again, and sure enough it says that we found 0. All right, let's try it a different way. Let's see what happens if we if 0 is our initial one. All right, so let's run that, and it still finds 0 as the min. So we've kind of got the two extremes covered, and we've probably convinced ourselves that we've got this okay. All right, so now the question is, why is this n squared? And again, the hint, or the thing to always look at, is to count our nested loops. And so we've got one outer loop where we're looping over all the numbers in A list, and we've got one inner loop where we're also looping over all the numbers in A list. So if our n is the size of A list, then we've got n times n is n squared in this list here. All right, but let's maybe prove that to ourselves by doing a little more complicated test. So let's import time, and from our random module let's import rand range, because what we're going to do is we're going to generate some we're going to do some testing here, and we're going to want to generate some big lists of randomly generated numbers. And so for list size in range, and let's start out with a list size of 1,000, and let's go up to 10,001, and let's go ahead and we'll grow the list size by 1,000. Okay, so a list here, we'll use a list comprehension, will be rand range. We'll get a number in the range, let's say out of 100,000 for x in range list size. So this little list comprehension here will create a list size number of randomly generated numbers coming from the range 0 to 100,000 minus 1. Now we'll get our start time. It's equal to time.time, and then we'll print out find min of a list, and then we'll get our end time, and so then we'll print, and we'll make this look kind of nice. We'll print size, come from our list size, and time will be a floating point number, and so we'll have list size and end minus start as the two values. Okay, so this will run for us, and we'll comment these two out so we don't have all this extra stuff in here. And so this will run over a bunch of test cases, and what we should see is the list size, the sizes grow, or the timings should grow quite dramatically as we go on. So let's see how that works. So at 1,000 we're at 0.07 seconds, at 2,000 we're at 0.3, at 3,000 we're at 0.6, so it looks like it's almost doubling every time, and 0.6 we're at 105, and then from 105 to 167 to 3.0 to 4.0 to 5.3 to 6.3. Okay, so that grows pretty dramatically from 7/100ths of a second up to 6.3 seconds, where our list size goes from just 1,000 to 10,000. All right, so now let's press on and let's look at a much more sensible option for find min, and we'll just redefine this here. Find min a list. All right, so this will be our linear function that we'll write. And now here's the difference here. We're not going to worry about comparing numbers against other numbers. In a linear approach, what we're going to do is let's assume that 5 is the minimum number in the list so far. All right, and so what we're going to do is we're going to keep track of a variable called min so far. And so the value of min so far will start out as being 5. So we'll compare 5 against 4. Is 5 less? What we're going to do is we're going to compare the number on the list against min so far. So is 5 less than our min so far? Well, 5 isn't less than 5, so that doesn't teach us anything new. So we move on to the next number in the list. Is 4 less than our min so far? Yeah, 4 is less than 5, which is min so far. So we've got to write this down. So 4 is less than 5, so we have a new value. So we cross out 5, we put in 4. Now we go on to 2. Is 2 less than min so far? Yep, 2 is less than min so far. So we crossed out 4, and we remember 2 as being the minimum number. And so on. 1 is less than 2, so 1 is our min so far. And we get to the end of the list, and in this case it's 0. So yeah, min so far is 0. Let's look at the opposite case where we had 0, 4, 2, 1, 5. So in this case, we start out with our initial min so far is being equal to 0. All right, 0 less than 0? Nope, so min so far doesn't change. 4. Is 4 less than 0? Nope, 4 isn't 0, so min so far doesn't change. What about 2? Is 2 less than 0? Nope, 2's not less than 0, 1's not less than 0, 5's not less than 0. So at the end of this trial, our min so far is the initial value that we started with. So that's exactly what we're going to do. We're going to initialize over here our min so far is equal to a list sub 0. And then for I in a list, and we just ask the question, if I is less than min so far, then min so far is equal to I. And when we're all done, then we return min so far as being our final value. Now, notice we only have one loop, no nested loops in this, and the loop is dependent on a list, so it's definitely going to be a linear order n algorithm. Alright, so let's just convince ourselves here. We'll uncomment these, and we'll go ahead and we'll let this run through this loop now. So remember, previously our times went from 0.07 over here at the smallest, all the way up to 6.3 at the largest. So if we come back over here now and we run through this again, we see very quickly for our first two test cases that we found 0, and then we see that Our time here for a list size of 1,000 was 0.00087, and that grew all the way to a whopping 0.00617. So a little bit of growth by by one digit order of magnitude there, but in general you see that this definitely does not grow very quickly, and it's definitely much faster than our initial kind of silly algorithm that we wrote here. Okay, so you might want to experiment with this a little bit more. You can take what we've done here, you can try running it up to even bigger list sizes. You could run the two in parallel with each other and print out the timings so that you can get a good comparison. You might want to even put these numbers into a graphing program, and for sure when you graph the values for the n squared min so far, you should see something that looks like a curve like that, and when you graph the linear algorithm you should see something that looks much more like a straight line. Alright, so that's all I have for this problem.